Hello, this is the Interim presentation for ME 452 or ISD 528, Analysis and Redesign of an RC Car. We are Team 2 consisting of members Justin Kim, Shuwen Yu, Anuj Raghavan, Sean Colling, Brandon Burlage, and William Hansen. For our product, we selected a self-driving RC car. This RC car enables students a unique opportunity to explore technology of the future in a much more accessible setting. The RC car functions primarily off of LiDAR and ultrasonic sensors in order to move on its own and is controlled by a Raspberry Pi controller. Based on market research, there is already a large market for RC cars as toys, and we estimate an annual production volume of 200,000 units. Our primary customers are STEM education classes, with secondary customers being RC car and hobby enthusiasts.
Okay, moving on to the functional analysis or the fast diagram of the RC car. The main functive is autonomous driving. There are many other functions, but ultimately this is an autonomously driving car. Looking into the primary supporting functives of the fast diagram, this ensures that the product targets our primary and secondary users, which include educating the user, making sure that this thing is constructible, and also entertaining the user. These functives also ensure that the car is reliable and also pleases the senses, which is noise reduction, and also looks visually appealing. Lastly, the non-primary supporting functives. These are more focused on the performance of the car itself, where it identifies and maneuvers the obstacle and also stores the energy.
We are proposing two different assembly processes displayed in the fishbone diagrams. Assembly process 1 consists of a ground-up approach with very little subassembly occurring in parallel, while assembly process 2 consists of an inside-out approach with joining together parts separately to form smaller subassemblies and then joining these together. In the first process, we start at the bottom with the car chassis and build off of there, adding the top battery cover at the very end. In the second process, we start from the middle, forming a subassembly of the motor and surrounding parts with the wheels, then attaching the subassemblies above and below from there. Assembly sequence 2 is preferred to assembly sequence 1 because it is easier to transfer, handle, and locate parts, and easier to test and assemble subassemblies in parallel, getting an overall score of 13 compared to sequence 1, which had an overall score of 8.
For the RC car function component mapping matrix, we have the functives from the leaves of the fast diagram being at the top row, as well as the components from the leaves in the fishbone diagram at the left column. Obviously, you have the most parts and the most important functives, that being the RC car to move, which would be turn right, turn left, as well as transmit force. We made sure that every part has a functive, as well as making sure that not one functive has more than 40% of the parts.
Next is the bill of materials. Here we see all of the parts used in the assembly of our RC car. Since our car is special and revolves around driving autonomously, the assembly includes parts that are not typical for most RC cars, such as the LiDAR assembly and ultrasonic sensors. The total cost for one car is $392.94. Compared to other RC cars on the market, prices range from $150 up to $500 for hobbyist cars. Our RC car's cost lands a bit high in the hobbyist market, although this price is inflated due to autonomous features. Redesigns for some of the more expensive assemblies will be crucial to reducing cost and having a competitive market price.
For our product family design, we constructed functional differentiation tables and component commonality tables based on the FAST diagram. We realized that the key difference between customer groups was educating a user versus entertaining a user. Based on this, the modules we selected were the wheel assembly, the motor holder, the LiDAR assembly, and the ultrasonic sensor assembly. This is because RC car enthusiasts might require more robust components for outdoor use or racing compared to a system that might be used in an education setting.
For the CAD analysis of the product family design, we created 3 component variants. This includes the sensor assembly, the wheels, and the motor holder. These are the main components that would change in an educational versus a hobbyist car. The hobbyist car would not be autonomous, so we would remove the sensors. It would also have nicer wheels and a motor holder that has a suspension system. On this slide, you can see the product family assembly diagram that is for the different assemblies with the different components for each.
That concludes our presentation. Thank you.